Okay, welcome to this week's first lecture. So in this first lecture, we are going to be solving one final example in mathematical modeling, and that is going to be an example related to control of a DC motor using a field-controlled DC motor. Okay, so remember, we control the DC motor in two ways. We have field control and armature control. And in armature control, we are changing the armature current while keeping the field current constant. And while using the field control, then we change the field current and we keep the armature current to be a constant. And in the earlier examples that we solved related to DC motor, we always changed armature current and kept the field current constant. So in this final example, we're going to be considering the reverse case. We consider a field-controlled DC motor. So our example is as follows. So I have here an amplifier with amplifying gain equal to A, and I have a resistor here and an inductor, and I have here the field voltage VF, and this is the field resistor, and that is the field inductor, and I have the field current equal to IF here. Okay, and in the armature side, I have the following circuit. So here we are said that IA is a constant. Okay, so as soon as you see something like this, you need to decide that this is a field-controlled DC motor. Why is that? Because we are changing the field current while keeping the armature current to be a constant. So remember, in the DC motor equations, we had the torque proportional to both the field current and the armature current. And in order to use the DC motor in a linear regime, what we are doing is that we are always keeping one of these currents to be constant, and we're changing the other one in order to be able to control the torque of the motor. So here, we are keeping the armature current constant, and the field current is changing. That is called field-controlled DC motor. So here the rest of the system is looking like this. So I have the shaft of the DC motor connected to a gear like this with gear ratio 1 to n, and this is connected to a load here. Okay, so I have the load here that is shown with the inertia J and with the friction constant B. All right. So now what I have to do is to define some variables. So here I'm defining, these are already defined in the question, so you don't have to think about defining those. But sometimes in some questions you might need to define some variables yourselves in order to be able to make things easier, like in the second example that we solved in DC motor. So here in this direction I have tau m, theta m, and omega m. And here I have tau L, theta L, and omega L. So here this m subscript usually denotes the motor constants, motor variables here. And this L subscript denotes the load variables. All right? So here this is our system, and in this case there is an interesting structure here. This variable theta L is measured by a device here, so I will call this as measurement and subtraction device. You really do not have to worry about what this is doing. So this is the variable theta L. We are measuring theta L. And here I have a reference theta value. So this is a position control system. So we are giving the system a position reference, angular position reference for the motor. And then we are comparing here the reference angle to the actual angle of the load. All right? And at this side of this device, I have gamma times theta r minus theta l. Okay, so you really do not have to worry what this is doing. What this is doing is just described by this equation. In this type of examples, if you encounter a strange component, that is usually doing a very, very simple thing, like here, this device is subtracting theta L from theta R and it's multiplying it with a simple gain gamma. All right, that is just a simple equation of this device. And here this is connected to the amplifier. So the amplifier is usually shown with these letters here. And I have connected the measurement subtraction device. The result of it is connected to the amplifier, which means that there is a voltage coming from here and it is going to be amplified by the coefficient A, and the result is going to be our field voltage variable. Okay, so when I look at this system, this theta r is a reference. So I want this load to stay at a single theta value, at a single angle value, and this is the desired angle value. It is given to the system as theta r, the reference variable, and we are measuring also the actual angle of the load as theta L, and we are subtracting these two variables and we are obtaining the so-called error variable, if you like. Then this gives us gamma times the error between the reference and the load, and the result is supplied to an amplifier, and this result is amplified by the coefficient A, and the result becomes the field voltage of the DC motor here. And here what we would like to do is to obtain the mathematical model of this system. So before I start with the mathematical model, I have to define what the input and the output of the system is. So here is what I'm going to do. So I'm defining the input to be theta r, the reference angle, and the output, the variable that we would like to control, is going to be the load angle. Okay, and that is the variable theta L. All right. Now the task is the same as the earlier examples, and it is going to be find the differential equation, transfer function, and state space representations. So let us now start writing the differential equations of this system. So I have the differential equation representation. I'm going to start from the left, and then I will write the relationship between VF and IF, and then from IF I will go to this torque, tau m, and from that torque I will go into the load torque applied by the gear onto the load here, and then I will go into the variable theta L at the end. And this theta L is going to be given to this device, and the equations are already given here. So there's minimum amount of work that I have to do on that side. But let us first start writing with the field circuit equation here. So here, once you look at this picture, you need to understand that this is a field-controlled DC motor, and what it is doing is that we are applying a voltage proportional to the error between the desired angle and the actual load angle to the field circuit of the motor, and the motor is then turning the load further depending on the sign of this error. Okay, if this error is positive, then the motor is turning to increase the load angle. If the error is negative, then the motor is trying to decrease the load angle by applying a negative voltage here. All right. So now let me start writing the field equation first. So L times, So the inductance times dIF over dt, this is the voltage on the inductor there. And if I sum this by the voltage on the resistor, I would get the total voltage here, which is Vf. So this is my first equation. And you see that there is a first order derivative in this equation. While writing such equation, I always try to keep the order of the derivatives to be at most at 1. This is because when I start writing the state space representation, then the first order derivatives would generally be quite useful to look for or find out what the state variables are. And here, by looking at this equation, I can actually understand that when I try to write the state space equations, one of my state variables can be just IF, okay? Because this equation is just trying to express IF dot in terms of IF and VF. And VF can be one of the state variables or it might not. It is going to depend on my other state variables. Okay? But because of this derivative, one candidate for one of my state variables here would become IF. So, and I'm going to do the same for the other equations. I will always try to keep the derivative orders at these equations at most at 1. All right? So this is my first equation relating Vf and If. Now let us go into tau m. So in the DC motor, I know that this torque generated by the DC motor is proportional to either the field current or the armature current. Here I am keeping the armature current to be a constant. Okay? So therefore tau m is going to be changing with respect to this changing field current. Okay? So that is why I'm going to put here a torque constant, k tau. This is a field controlled DC motor. So I would put a superscript f here. And then this is going to be multiplied by IF. All right? So this is the torque generated by the DC motor, which is proportional to the field current, because this is a field controlled DC motor. And then I will try to go into the other side of this gear here. So I have tau L and tau M are going to be related to each other with a really linear relationship. And I can also write theta L in terms of theta M using the gear equations here. Okay? So here, this gear ratio is 1 to n, and the radius of, this is n, and the radius of this gear on the load side is larger. So if I try to write the equation for theta L and theta M, then I would see that if I rotate the first gear by theta M, theta L is going to be smaller if n is larger than 1. Okay? That means that I need to put here the coefficient 1 over n. If n is larger than 1, then theta L is smaller. If n is smaller than 1, then theta L is going to be larger. And once I put the coefficient for the thetas here, then what I can do is I put the reverse coefficient into the torque equation. So I would have just this n coefficient in front of tau m. Okay? Now I'm ready to write the equation for the inertia, and that is going to be J times, I need to write here theta L double dot, but I want to keep the derivative orders in my equations to be at most 1. So I really do not want to write here theta L double dot. Instead, I will use the equation theta L dot is equal to omega L here. So that is why I'm going to write J times omega L times omega L dot, which is going to be the same thing. We know that omega L is theta L dot, so omega L dot becomes theta L double dot. Okay? So this is my term on the left hand side, this is inertia times the angular acceleration. It needs to be equal to the net torque applied onto this inertia by the outside elements. And I have tau L here applied onto this inertia. And I would have also the friction element here. It is going to be minus B. If I write this equation in terms of theta L, then I would have put here theta L dot. But really here I'm using omega L as my main variable. So here, instead of theta L dot here, I write just omega L. Okay? So that is my equation relating tau L and omega L. And finally, I write the equation theta L dot is equal to omega L here. And you see that in this last equation, the derivative order is also 1. So when I look at these equations, I can see some candidates for my state variables directly. IF is one of the candidates, omega L is one of the candidates, and theta L is one of the candidates. Okay? Because these equations are expressing the first order derivatives of these variables in terms of some other variables. So my candidates for state variables by looking at these equations would be evident to me, and these are IF, omega L, and theta L. But still I need to know what the order of the system is in order to be able to decide on the number of state variables. So if the number turns out to be 3, then I'm fine here. So it is going to be just these 3 variables. If it is more or less, we are going to see. So here I can actually write one more equation. Omega L is 1 over n times omega m. It really doesn't matter. You're going to see that we won't be using these two equations somehow at the end, but these are the equations relating this omega L to omega m. How did I obtain this equation? This 1 over n is a constant here. So if I take the derivative of these terms on both sides with respect to time, then this becomes theta L dot is equal to 1 over n is a constant theta m dot. Theta L dot is omega L, and 1 over n remains here, and theta m dot is omega m. All right? And what about the rest? The rest is going to be not really difficult. So I have already obtained a theta L here. I came from VF from here. I went into tau M to tau L, and then I went to omega L, and I went to theta L. And then what is going to be remaining? VF is going to be equal to the voltage here, and that is going to be gamma times theta R, theta minus theta L times the amplifier gain A. All right? Well, this is equal to A times gamma times theta R minus theta L. And this actually completes all of the equations that I can write for such a system. So this completes differential equation representation. A time domain representation which is written in terms of differential equations. So this is my differential equation representation. So now I'm going to go into transfer function representation, which is going to be in Laplace domain. For that, I'm going to use the concept of a block diagram. And in order to be able to form my block diagram, this is what I'm going to do. So I'm going to start here from my input variable. So I will put here my theta R, and at the end, I will have my output variable, theta L. Okay? And then I need to fill in the forward path transfer function here. Okay? Going from theta R, maybe I should put it a little bit towards left so that I have more space. This is theta R, the reference theta, and I need to go to the output variable theta L here. Hopefully I will have sufficient space here. So I have already gave you some hint about what I'm going to do here. So I'm going to go I'm going to start from this equation. Okay, so here I see that I can actually obtain what VF is from theta r using this equation. Okay, but you see that from this equation, in this equation, I need to subtract theta L from theta r. So I don't know what theta L is here at this stage on the left. So that is why I'm going to put here a missing variable, theta L, that I would not know until I come to the end of this block diagram. Okay, so here is going to be my difference, theta r minus theta L. Okay, I know that if I multiply this signal with the gain A gamma, then this is going to be the variable VF. Okay, so I have obtained the field voltage variable here on the left hand side. And what can I do next? I can actually go from VF to IF. But how can I go from VF to IF? There is going to be a system here in Laplace domain. Okay? What is the transfer function of that system? Connecting IF, the field current, to the field voltage. Okay? So I want you to pass this equation into Laplace domain and extract from that equation what IF is in terms of VF. If I pass this equation into Laplace domain, it's going to be Ls plus R times IF is equal to VF. If I extract IF from that equation, you're going to see that IF is going to be VF, capital VF, divided by Ls plus R. Okay? So that means that this missing system that I need to have here is going to be just 1 over Ls plus R. Alright? Now, and this means that between VF and IF there is the system 1 over Ls plus R, a transfer function like this. And after IF, I can go to tau m by multiplying IF with a single constant k tau f. K tau f. Okay? So this gives me tau m. Alright? The torque generated by the motor. Then by multiplying tau m with the gear constant n, I can obtain the load torque. So I put here n, and this becomes tau L. Okay? And from tau L, I can go into omega L. Okay? So this equation is only related to omega L and tau L. And here, I can pass this equation into Laplace domain, and I can try to extract what omega L is in terms of tau L. Okay? So I will put here another system block, and that is going to give me omega L. Alright? So I want you now to pass this equation into Laplace domain in your mind. And while trying to do that, just try to express omega L, capital omega L, in terms of tau L. Okay? If you try to do that, you will see that this is going to be Js times omega L plus B times omega L. So I have here on the left Js plus B times omega L, capital omega L, is equal to capital tau L. So if I extract omega L from there, I would get omega L equals to tau L over Js plus B. So I would have here 1 over Js plus B as the missing system. Okay? That is the transfer function between tau L and omega L. And the only thing missing here is to pass from a system which passes from omega L to theta L. Okay? And that is going to come from this last equation. So this equation expresses theta L. It can be used to express theta L in terms of omega L. So there is going to be another missing system here, and it is going to give me theta L from omega L. Okay? Now I want you to pass this equation into Laplace domain in your mind and express theta L in terms of omega L. Okay? So it gives me S times capital theta L is equal to capital omega L. So if I express theta L, capital theta L, in terms of omega L, what am I going to multiply omega L with in order to be able to find theta L? And it's going to be the system 1 over S. All right? So I would just have here the system 1 over S while passing from omega L to theta L. And this completes the forward path transfer function for this block diagram. Okay? The only thing missing here is this missing variable that I did not connect anywhere. So this is my subtraction variable theta L, which is the output, and theta L is here at the end of the block diagram. So what I'm going to do is just connect this theta L into the feedback path. So this actually completes my block diagram representation, and now by using this block diagram I can find the overall transfer function of the system. Okay? So how can I find it? So this is only a single feedback loop, and in order to be able to find the overall transfer function of it, I can use feedback rule. All right? So G of S, the overall transfer function of this system, is going to be the forward path transfer function divided by 1 plus 1 everything in the loop. Okay? So what is the forward path transfer function? These are all serial connected blocks. So the forward path transfer function is going to be the multiplication of all of these blocks. All right? So I would have here A times gamma times K tau F, and I have N here. These are everything in the numerator, divided by Ls plus R and Js plus B, and I will put an S here, which is this S. Okay? This is everything in the forward path transfer function, multiplication of all of these blocks, divided by 1 plus, this plus is because of the negative feedback, and if I had a positive feedback here, if this minus sign was plus, then I would put a minus sign here. And this is going to be 1 plus everything in the loop. But we see that the transfer function in the feedback path is just 1. There is no block in the feedback path, which means that the transfer function from here to here in the feedback path is just 1. Which means that everything in the loop is just going to be equal to the forward path transfer function once more. So I have A gamma K tau F N divided by S Ls plus R Js plus B, and now in your mind here again I want you to equate the denominators in the denominator. Okay? If you equate the denominators in the denominator, then this is going to go to here. It's going to be summed by this thing. But when I equate the denominators there, this denominator is going to cancel this denominator in the numerator. Okay? So the result is going to be A gamma K tau F N divided by, I will have this thing S Ls plus R Js plus B plus A gamma K tau F N. I'm really sorry I had to write quite small here. I hope you can zoom here and see what these terms are. But this is my overall transfer function here. All right? So we have found the overall transfer function of the system. And what is this? This is just the ratio of the Laplace transforms of the output, theta L of S divided by theta R of S. This is my definition of the transfer function. Ratio of the Laplace transforms of the output to the input. So now we have completed the transfer function representation here. That is our transfer function representation, this G of S. And now the only thing remaining is to find the state space. So if I put here, this is going to be the transfer function representation. So the state space representation is going to follow. When I start with the state space representation, the first question that I need to ask is how many state variables I would need. And in this case, I can answer this question by looking at the order of this system. And I can I can find out the order of the system from the transfer function by looking at the largest power of s in the denominator. So here, if I look at the denominator of this transfer function, I see one s here, one s here, and one s here. And that means that the largest power of s in the denominator is just 3. That means that this system is a third order system. Okay? And that is going to mean that if I want to find a state space representation for this system, then I need to use 3 state variables. So what are these state variables? Remember, a state space equation is just an equation in this form. And in the state equation, what we are trying to do is we are trying to express the time derivatives of the state variables as a linear combination of state variables themselves plus the input. So what I have to do is to look for equations here that would express the first order derivatives of the state variables as a linear combination of state variables themselves plus the input. And here I would go back to these equations. And remember what I told you. Try to look for derivatives here in these equations, and then you are going to find your state variables automatically. I need 3 state variables, and then I would need to express time derivatives of these state variables in terms of the other variables. So this equation expresses time derivative of if in terms of other variables, and this equation expresses time derivative of omega L in terms of the other variables, and this equation expresses time derivative of theta L in terms of the other variables. So whatever I have to do, I would need to use these 3 equations here. Okay? And then what would be my state variables? They would be if, omega L, and theta L. Here, you don't have a unique choice. Instead of choosing theta L, for example, I can choose theta M as my state variable. And if you do that, you will be able to find another state space representation, but it is going to be in some way equivalent to the original state space representation that we would find. Because theta L and theta M are related to each other with a linear relationship like this. So there is really no difference between choosing theta L or theta M as your state variable. Just your state space equations would be different just a little bit, but everything would be fine. That would be also a valid state space representation. Remember here, state space representations are not unique. And once you choose your state variables, you have to find a unique state space representation for those state variables. If you change your state variables, you will find another state space representation for the same system. That is equivalently fine. There is no harm in that, but sometimes choosing some state variables would make things easier for you. And here, choosing these variables, if, omega L, and theta L, I see that allows me to use these equations directly, which makes things easier for me. But as I told you, instead of omega L or theta L, I could equivalently choose omega M or theta M as my state variables. So let me erase this part. So here my selection is x is defined as, this is my definition sign, equality, and there is a triangle on the top. This is the definition of the state variables. X is defined as I'm choosing if, and I'm choosing omega L, and I'm choosing theta L as my state variables. So here an equivalent choice would be to replace the places of these variables in the state vector. That would also change your ABCD matrices that you would find here, but that would be also an equivalent state space representation. It is also one of the infinitely many state space representations that you can find. So not only the selection of these variables, but the order of these variables would determine your state space representation uniquely. All right? If you change the places in the state vector, then you would obtain a different state space representation as well. So now let us try to write the state space equations. I know that for the first state variable, I need to express if dot in terms of the other state variables. For that, I'm going to be using this first equation. L times if dot, this is equal to, it is this term. You see that I can take this RIF to the other side by multiplying it with a minus sign. In one of the earlier examples, I have forgotten this minus sign here. I added into the description of the video that there was a mistake there. So in the first example, probably related to the DC motor, this minus sign is missing, which was a mistake. This is R times IF, and I would have here plus VF, okay? But VF is not really one of the state variables. Remember, I need to express the derivative of the state variables as a linear combination of state variables plus the input. VF here is not really one of the state variables. Therefore, what I have to do is I need to write it as a linear combination of state variables and the input. So here I will go to this equation. VF is just written as a linear combination of input, which is theta R here, and one of the state variables, which is theta L. So I would add here plus, instead of VF, I write the right-hand side of that equation. A gamma times theta R minus theta L. Okay? So this is going to give me my first state equation. And you see that on the right-hand side, I only have state variables or the input. And now let us use the second state variable, omega L dot. In order to write my second equation, I will use this equation. J times omega L dot is equal to, the right-hand side is tau L minus B omega L. B omega L is fine. It's a linear combination of the state variables, but tau L is not a state variable. Therefore, I need to express it or try to express it in terms of my state variables. And I have here tau L is N times tau M, and tau M is K tau F times IF. And IF is one of my state variables. So instead of tau L here, I write N times K tau F times IF. Okay? This is a linear combination of my state variables, one of which is IF. So then I have then the rest of the equation minus B omega L. Okay? Omega L is already one of the state variables, so I don't have to change anything in that second term. And the last state equation is going to be given by this equation, and that is going to be theta L dot is equal to, I really do not have to change anything there because the right hand side is already a linear combination of my state variables, one of which is omega L. So these are going to be giving me my state equations. Let us now write my state equations. X dot is equal to, will have a 3 by 3 matrix here, times X plus B times U. And this U here is nothing but my input, and that is theta R in this system. Okay? Now let me write the first equation. First equation is expressing IF dot in terms of my state variables and the input. IF dot, the coefficient of IF in that is minus R over L. Coefficient of omega L, there is no omega L term in the first equation. And coefficient of theta L is going to be, I have minus A gamma divided by L. There is a minus sign here. And what about the coefficient of the input? The theta R coefficient on the right hand side is A gamma divided by L. Maybe I should write it correct. So it is like this. Let us go into the second equation, omega L dot. I need to express omega L dot in terms of the state variables and the input. Input coefficient in the second equation is 0, and the input coefficient in the third equation is 0 on the right hand side. So here, for the second equation, coefficient of IF on the right is N times K tau F divided by J, N K tau F divided by j. Coefficient of omega L is minus b over j, and coefficient of theta L is 0. And finally, the third equation is going to be theta L dot is equal to omega L. And the coefficients are 1, 0, 0 here, and there will be a 0 there. And what about the output equation? The output equation is really simple. The output is one of the state variables. That means that that equation is going to be easy to write, du. There is no input component there. And the output is theta L. It is a third state variable, which means that I will put a 1, 0, 0 here. Okay? And that gives me my state space representation. So this completes this example. We have found these three different representations for the same system. So in the next part of the course, we will be using mostly the transfer function representation. Only at the end of the course, we will start using a state space representation for the system. And actually, we will see at the end of this course that using state space representation is a state space representation is a much more powerful tool than a transfer function representation, because it can actually manage multiple input, multiple output systems. So but that is going to be all for the mathematical modeling part of this course. And from this point on, we're going to start with using the transfer functions, and we're going to start to understand what a control system is, how we can obtain the output of a system for some simple inputs, and we're going to learn about some performance measures that we can actually measure the performance of a control system with. But this is going to be the topic of time domain analysis, which is what we're going to start with in the next lecture. But that's all for this one. Thank you for watching.